So welcome back to the webinar, guys. Now we have a problem on condensation. So condensation typically means cooling of a vapor on a surface which is at a much lesser temperature than the vapor itself. So now in this case we have a problem in which we have a vertical plate which is 0.4 meters in height and 0.3 meters in wide, which is exposed to a saturated steam at 40 degrees Celsius in atmospheric pressure. You are going to find the film thickness at the bottom of the plate, the maximum velocity at the bottom of the plate, and the total heat flux to the plate. So now let's write the given data first. So the height or length this is 0.4 meters, the width 0.3 meters, the surface temperature or the wall temperature is 40 degrees Celsius. So what are you going to find? You will be attempting to find the film thickness, the maximum velocity Umax at the bottom of the plate, and the total heat flux Q. So now let's solve this problem. So the problem states a plate is being exposed to a saturated steam which is at a temperature of 40 degrees Celsius. So it means that steam is going to condense on this plate. So you have to know that steam is at a much more higher temperature than the plate. So the steam is going to get condensed over the plate. The Tsat of the steam, saturation temperature of water, is 100 degrees Celsius. So please look into the properties of water. At 100 degrees Celsius, from the steam tables, page number 4, you just have to find the HFG value, 2256.9 kilojoules per kg, so which is 0.9 into 10 power 3 joules per kg. So please remember that substituting in kilojoules is a crime, so please convert it into basic units. So now we know that the film temperature is going to be TW plus Tsat by 2. So the wall temperature is 40 degrees Celsius plus 100 degrees Celsius divided by 2. It's going to be 70 degrees Celsius. So now for this 70 degrees Celsius, we are going to find the properties of saturated water. So this could be gotten from the HMT data book, page number 21. So the values that you have to look into: rho 979.5 kg per meter cube. The kinematic viscosity is 0.421 into 10 power minus 6 meter square per second. The thermal conductivity is 0.66 watt per meter Kelvin. And the dynamic viscosity, as usual, you can arrive at by multiplying rho and nu, so which is 0.5 into 0.421 into 10 power minus 6. So this will be 4.12 into 10 power minus 4 Newton second per meter square. So now we have got all the properties of saturated vapor at 70 degrees Celsius. Now you should go to the HMD data book. So page number 148 from your HMD data book. So from there you will see that the thickness is 4 mu k x into T sat minus TW divided by G into H of G into rho square whole power 0.25. So this relation you could find it at page number 1.48. So now in this equation we are going to substitute the values noted down from the data book. So 4 into 4.12 into 10 power minus 4 into 0.66 multiplied by 0.4, which is the length of the plate. We are substituting the length of the plate for x, and then the T saturation temperature 100 and the wall temperature 40 divided by 9.81 into H of G into density square 79.5 whole square, sorry about that, and 25, so which works out to 1.87 into 10 power minus 4 meters. So this is going to be the film thickness at the bottom of the plate of length 0.4 meters. Now the second subdivision, which is the maximum velocity, so which is U max is equal to rho g del x squared by 9.81 1.87 into 10 power minus 4 whole square divided by 2 into dynamic viscosity 4.12 into 10 power minus 4 is the value we got already. So Umax will be 0.407 meters per second. So this is the maximum velocity at the bottom of the plate. So now we will move on to find out the heat transfer Q. So for this you need to first find the average heat transfer coefficient H. So this can be obtained from HMT data book page number 148. So this equation is available, so which is 1.13 into K cube into rho square into G into H of G divided by mu into L into T sat minus TW power 0.25. So now we have to merely substitute the value cube into 979.5 square into 9.81 into HFG 2256.9 into 10 power 3 divided by dynamic viscosity 4.12 into 10 power minus 4 into length of the plate 0.4 into T sat 100, wall temperature 40, whole power 0.25. So now we just have found out the value of H, which is 5633.22 watt per meter square Kelvin. Please do the calculations in the calculator carefully, very carefully. So now Q will be HA delta T. So this will be H into the area is going to be the product of length and width, and delta T is going to be the difference between the saturation and the wall temperature. So now we have 5633.22 into length of the plate is 0.4 meters, width is 0.3, 100 minus 40. So the net heat transfer is going to be 40,559 watts. So this is the answer.